I'm recording this video to elaborate further the definition of a work done integral that I introduced in class today. As you recall, the work done over a curve is defined as an integral here from A to B of the dot product between the force vector and the velocity vector. To understand why this definition is consistent with our conventional definition of a work done along a straight line, let's take a little digression here. You may recall from your project 1 that the arc length S is also defined as an integral from point A to point B, okay, of the magnitude of the velocity vector so let me write the arc length integral this way. Now, using the fundamental theorem of calculus, you can deduce that the differential ds here is the same as the magnitude of the velocity vector times dt. Okay, so we're going to use this very shortly. Okay. Meanwhile, let me go back to the dot product inside the work done integral. Now, to help you see a little better what this dot product is telling us, I am going to rewrite this velocity vector slightly differently. Okay. In particular, I'm going to single out its magnitude and multiply by a unit vector pointing in the same direction of the velocity. In project number 2, you will learn that this vector capital T as the unit tangent vector. Okay. So this same dot product, okay, can be rewritten as the force dot product with the unit tangent vector followed by the magnitude. Okay, so let me erase this part here. Now that you see the denotation, and I will throw back the integral in this case. Okay, so this is the same as integrating from A to B of the dot product between the force vector and the unit tangent vector times the magnitude of the velocity vector times dt. And probably you recognize that this is just our differential ds. Okay, and this guy here is just the component of f in the direction of motion. Okay, So now you are singling out the component of the force vector multiplied by the infinitesimal arc length, okay? And in that sense, it is consistent with our conventional definition of the work done, okay? And the integral simply sum up all these little pieces for us, okay? I do not normally introduce the work done integral this way, but you may find this approach a little bit more comprehensible, even though it is not the most efficient way to do computation for us, okay? I will elaborate a little bit more later on this semester, but for now, I am going to stick with the working definition that I introduced earlier today in class. Okay, see you on Thursday.